So this is an explanation of the phase changes and temperature changes. So we will start out with a simple chart. So this is time and temperature. And we watch if we take a solid below the freezing point and heat it up, we will come up with a graph like this. As it starts to melt, it'll level off, and then once it's all liquid, it'll start heating up again. And as it starts to boil, it will level off, and once it's all gas, it will heat up again. So what we find here is this region is just solid. This area is solid and liquid. This area is just liquid. This area is liquid and gas. This area is just gas. Move in just a little bit there. These regions where we only have one phase present, so the solid areas, the liquid area, and the gas area, we see a temperature change because all of the energy that goes into that system is going to increasing the thermal energy of whatever is present. So we see temperature changes when we have one phase. So that's here, here, and here. In these other two regions where we flatline in the temperature, meaning that the temperature stays the same, all of the energy is going into the phase energy, or converting all of the solid to liquid or the liquid to gas. If we were going the other way and cooling the system down, converting all of the gas to liquid or the liquid to solid. So these are called phase changes, and they occur here and here. Again, where the temperature flatlines and all of that energy is now going into the phase change instead of the temperature change. All right. Couple of things that are also useful along this line. If we start down here at the bottom, we have very slow moving particles. And as we increase temperature, we get faster moving particles. So up here we have fast moving particles. Another important thing to discuss would be arrangement of particles. So we have particle arrangement. This is basically the pattern or rigidity or organization of the particles in the sample. Solids will have a very clear pattern. We consider them stuck in place. They will vibrate back and forth, but they're not actually allowed to move around. They can bounce back, very small amount of space for them to move. Liquids, they can move around, but they can't move everywhere. We say that they are contained in liquid. we use the reference to the classroom. So when you are seated at your desk, you are acting like a solid where you're stuck in one place. You can move, you can reach across your desk, you can reach side to side, you can turn in your seat, but you're pretty much stuck in one place. The liquid would be more like what we would do in the lab space, where you have a little bit more movement, but you're pretty contained. You can't really move. You can't go outside of the classroom. You're stuck in one particular area, but you can still move around. Now, gases, that's more of like what happens after school. You can go anywhere. You're free. And gases really do behave that way. They literally can go all over the place. So the arrangement or the pattern, the organization, it's definitely much more organized in the solid. We have a clear pattern. They're stuck in place. Liquids, they can move around a little bit more, but we consider them to be contained. And then gases, since they can go anywhere, we consider them free. The last part that I wanted to kind of specify with this is how do we get from solid to liquid, and the terms we use to go to explain what's happening here at these phase changes. So we'll move around up here closer to the top, and we say that if we're going from a solid to a liquid, we refer to that as melting. Going from a liquid to a solid, we say freezing. And we should remember this from our videos that we've seen, and also what you see in your real life, where you watch or you put ice or water in an ice cube tray, stick it in the freezer, and it's going to freeze. If you pull those ice cubes out, they're going to melt, just like, say, ice cream melts or chocolate melts on a hot day. If we're going from liquid to gas, we call that evaporating. A more common term is boiling. And gas to liquid is condensing. And this we see a lot on our drinks. If we have a really cold drink in the middle of the summer and we're walking around, you may notice some drips of water on the outside. It's that those the water particles in the air have cooled down because they've touched the cold drink and they've turned to liquid around the outside. A lot of this is called also sweating. If you've heard somebody saying that, oh, my drink is sweaty, that's what they're talking about, is this condensing. So if you're an ICP, that's all that you really need to worry about. If you're in chemistry, we've gotten kind of into the math of this. So with the phase changes, that's what I'm going to talk about now, is the equations we use with these to calculate the change in energy used for these. So for phase changes, it's energy equals mass times heat. And we have Q for energy, M, and H. We know that it takes more energy to go from liquid to gas than it does to go solid to liquid. So down here, it takes less energy, so we need less heat. And that is where we use Q equals MHF, or the heat of fusion. For changing liquid to gas or gas to liquid, this takes a little bit more effort because gas has so much more energy than liquid or solid. We need to use Q equals mHV, or the heat of vaporization. That's how we calculate the energy used to change a phase. It's different than the energy used to heat or cool a substance. So if we're dealing with a temperature change, we use Q equals mc delta T, or energy equals mass times the specific heat times the change in temperature. And to get change in temperature, we do final minus initial. A little off the screen there. Final minus initial. So the specific heat is specific for the substance, water, or metal, or even different types of gases have different specific heats. And they're also for the phase. So when you're dealing with solid water heating up, that's going to have a different C than liquid water heating up. All of these numbers, the H's and the C's, will be given to you in on your homework papers or in labs, or you will be looking for that number. I believe that finishes up. So again, if you are an ICP student, you don't need to worry about the equations, but chemistry students need to have a good grasp of how to use these equations.